Okay, I want to thank everyone for joining us this morning. This is our first in the series of Nastran In-CAD webinar series. My name is Andrew Sotterelli. I'm a technical support specialist here at Autodesk, and with me this morning is Bart McPheeters, who's a senior technical specialist for FEA products. So as I mentioned, this is the first in our Nastran In-CAD series for webinars. For those of you familiar with our other simulation products, we've been doing for the past year or so Build Your IQ webinars for simulation mechanical, simulation mold flow, simulation CFD, and we've also done periodically some Nastran webinars during the simulation mechanical slots. So some of you may be familiar with our August webinar on Simulation Mechanical 2015 R1, which added in a lot of new Nastran functionality, as well as our October one from 2014, where we went over some basics of Nastran In-CAD for simulation mechanical users. We'll be doing these webinars every other Tuesday at 11 a.m. Eastern Standard Time, going over different topics about Nastran In-CAD. So this week we'll just be doing the basics, what is Nastran In-CAD and some fundamentals for FEA. But in the future we'll be talking about contacts and constraints, composite analysis. We'll also be having a webinar in May with Mitch Muncy, the product manager for the Nastran product line, going over what's new in the 2016 products. And those products are available. They launched on April 7th. So those will be available on Autodesk accounts if you have the correct entitlements there. So we do announce these webinars on the Autodesk Nastran In-CAD forums. We do it through LinkedIn, Twitter, and our Facebook page. And as always, the downloads or the recordings for these webinars will be available on the Autodesk Sim 360 YouTube channel. Usually takes us a couple days to get those uploaded, but if you want to take a look at them, they should be there by the end of the week. And as I mentioned, Nastran In-CAD 2016 launched on April 7th. So if you haven't had a chance to take a look at that yet, highly recommend it. There are some great performance enhancements there for those users. In Inventor, we transitioned the product into an environment rather than an add-in. So we saw a lot of speed up and enhancements there to user workflows. So at this point, I'm going to turn it over to Bart here, and he'll be doing just an introduction to Nastran In-CAD as well as some FEA fundamentals.
Do we want to do the polls first or last?
So yeah, we can kick off a few polls here.
I have a couple questions to ask people so we know who's listening to us.
So here we're just looking, how would you classify yourself? Are you a designer? Are you an engineer? Are you an advanced FEA analyst? Maybe you're a student, or maybe you're a manager or some other role within an engineering organization. So take a couple seconds there and vote. We've got almost everyone here voted, so we'll give it another 10 or so seconds.
Engineers and others are our primary category today. Okay.
All right. So let's share that. Yeah, so it looks like a good chunk of you are engineers, and then we got a good chunk as well as other. So let's go ahead to our next. And all right. And what CAD packages are you guys using? Using Inventor, SolidWorks, CATIA, Creo? Maybe using something else like Rhino or Solid Edge. So take a couple seconds there and let us know. It looks like most of you are using Inventor.
No surprise there. Although a fair number of others.
And we'll go ahead and share those. So it looks like 86% of you are using Inventor and 14% using something else. All right, and the last and most important poll here. Have you used Nastran In-CAD before? So hopefully you guys have all maybe opened it up and taken a look at it.
lot of people have taken a look at it. That's good.
All right, and we'll go ahead and share those results.
But a good group who were at the right show here.
Yes, I think we've got the great, majority of you have used it just a little bit, or you're interested in learning about, what is Nastran In-CAD. So I think this will be a great webinar series for you. At this point, Bart, if you want to take over.
Okay, let me organize my screen here a little bit, and I'll jump right into the presentation. Okay, I'm going to start off and just quickly, what is Nastran In-CAD? For those of you who said, what is Nastran In-CAD? This is good. I'm glad we're doing this. A quick slide or two on where In-CAD fits into the Autodesk product and simulation portfolio. And then I wanted to talk just quickly on, I call it my 5 slides on everything you ever wanted to know about finite elements that you forgot from school or never had at school if you're like me. I'm going to talk about what you can do in finite elements, what you can do in In-CAD, from simple things to amazing things, and then I have a little demo of a problem that I think illustrates doing a simulation in In-CAD and how it all works fairly easily. So, without further ado, what is In-CAD? It is a general-purpose finite element analysis tool embedded in your CAD system. It is embedded at the moment in Inventor, which is why which is an Autodesk product, so that's an important one. But it's also embedded in SolidWorks. So if you or people are using SolidWorks, In-CAD is available, and it's the same basic interface and the same tool. You have the benefits of being a CAD embedded tool, namely that you can update the CAD and quickly update your simulation quickly. The licensing is flexible and open. It's the same as all the Autodesk products. You have many options with that. Behind the scenes, we're running Nastran. It's Autodesk Nastran. We're running that in the background, not a code that nobody's heard of. It's one that people have heard of. And In-CAD has a wide range of simulation capabilities, and I'll sort of go through some of those as we get into our presentation. The simulation suite that Autodesk has ranges from designers who are doing really design work and just a tad of simulation, all the way up to analysts who do nothing all their day but do simulation and finite element work. So we our Inventor professional product that sits inside of Inventor, does a simulation, does a limited number of things, and I'll talk a little bit about that, is really for people who are doing the occasional analysis and needing to do things like that. Our simulation mechanical product that's been around for several years, the blue arrow here, is sort of a higher end product. It's sort of its own pre and post processor. It's a standalone sort of product, and you can do a lot of really top end stuff with it. Doesn't quite go all the way up to where the analysts are going, but it does a lot of good stuff. The Autodesk Nastran is a standalone product on itself, and its top end analysts can do whatever they want with that. It sits in the same market as some of the other big general codes, the other Nastrans and ANSYS and Abacus. In-CAD, on the other hand, is back down here. It's providing sort of a link between the occasional users, and it's giving the occasional users who have minimal requirements a lot more capability to do, but because it has a fair number of capability and it's embedded in the CAD, it's extending up into the simulation mechanical range some more. So there's a number of things it fills in. I'll say it fills in a gap between simulation, Autodesk Inventor Pro, and simulation mechanical. So these are our products that we go through here with little animations on them. Okay, finite element basics. When do you need finite element analysis? Why would you need it? If I have a plate up here like on the top, it is a square plate. The stress in the plate is the total force I've applied divided by the cross-sectional area of the plate. Hey, I don't need anything but a hand calc to come up with that answer. So that is not where I need finite elements. The second equation, I have a hole in the plate. I can use this with finite elements, but alternately, I can do the F over A and multiply it by a stress intensity factor, a KT, and I can dig that KT up from some textbook like Rourke or a machine design handbook or Mark's handbook, and that'll give me the stress. So if I've got a plate with a hole in it, regular uniform tension or something sort of like that, I don't really need finite element analysis either. I can use it, but I don't need it. Once I start putting more holes in here, I can do my KT equation and come up with some rough ideas, but if I want to know the actual stress in the tendons and how the load is transferred around through these and where the high stresses are, I can get some ballparks using hand calcs, but it's complicated enough that my finite element is the best choice to do something like that. So how does it work? Obviously, on the previous slide, once we had our complex shape with all the holes in it, there's no closed form solution for it. But, as on the top one, I can solve closed form solutions and get answers for simple shapes. So the whole point of finite elements, and that's why they're called finite elements, is you break up a complex, infinitely variable shape into a finite number of simple shapes. And then these simple shapes can be tetrahedrons, triangles, quadrilaterals, beams or rods. These are all finite elements. And the computer absolutely excels at taking lots of simple shapes and solving those equations all at once. And basically that's, in a nutshell, finite element breaks complex into simple, solves the simples all at once. In the simplest terms, a structural problem, a static formulation, can be formulated with a pair of nodes, these are big red dots, separated by some stiffness. Here it's represented by a spring. If I apply a force to the two ends of these and push on it, it'll deflect some amount. So knowing my applied force and knowing my stiffness of the spring down here, I can solve for the displacement and find out how much these two nodes move towards each other. And that's structures. In FEA, everything is a system of equations because every element is its own little equation. If my whole model were consisting of spring elements, it would hold me a whole bunch of equations exactly like this. So I have a column vector of forces, one of which are applied at all the nodes. I have a stiffness matrix, which represents the stiffness between these nodes, multiplied by the displacements, which are unknown. So using matrix techniques, I can solve for the unknown displacements given my knowns. So displacements are what I solve for. The finite element mesh, as I've already mentioned, consists of nodes, which are 3D points in space, and those are the x locations, and we don't know where they displace, but we know where they are. The elements themselves are areas or volumes or lines down here defined by nodes, and those define the stiffness terms for the equation. So how one end of a beam relates to the other beam is a stiffness relation, and that's the K term, and it's just more complicated for some of these others. So when I create an element in a finite element, what I'm doing is building a little stiffness matrix that says these corner nodes will relate to each other with a stiffness related to how stiff my formulation for my element is. So when I solve the problem, I get these corner displacements, and knowing the stiffness, I can get things like strains and so on. The element formulation, i.e. when I build the stiffness matrix down here, it also provides a relationship between the displacements and the element strains. So on the next slide, I have my unknown displacements, which I've now solved for, and I can use a B matrix, which is a strain displacement matrix, that gives me the strains in the individual elements. This B matrix is usually a very, very complicated matrix, especially if you're using quad elements or hexagonal elements or P elements. The B element is the element formulation for the most part, and every finite element code guards how they calculate those B matrices very carefully because it's sort of their proprietary edge over the competition is we calculate a better B matrix than someone else. They can use that to brag. Once I have those strains in the element, I can transform the strains into stresses through a material matrix. G is a material matrix. The very simplest G is a modulus elasticity. since stress equals the modulus of elasticity times the strain. If you're on a linear curve, it's just the slope of this linear stress-strain curve. But you can see from this that I'm solving for the displacements, and the displacements determine the strains determine the stresses. So if I'm calculating displacements incorrectly, everything else is going to be incorrect too. That's just the way it is. So you're not going to get good stresses if your displacements are wrong. So where do we use FEA? In design, there's two particular ways. You have a part and you can predict its performance for planned use, or you can predict its potential failure with predictable abuse. Certain things people know they're going to do. Cars, for instance, you're going to drive, say, 100,000 miles and it's going to be shaking and vibrating, so I can use FEA to simulate what driving a car is going to load my parts. Similarly, people are going to abuse things. They're going to drop cell phones. So I can do a failure analysis dropping my cell phone to predict, is it going to survive that abuse? Additionally, outside of the design world, there's a lot of forensic finite element analysis going on. Something has failed. You want to figure out why it failed and what you need to do to make sure it doesn't fail again. Similarly, I can improve performance. I have a part that does something, but I may be able to make it do better, or I may be able to make it safer by some kind of analysis and figure that out. I may have a part that weighs too much or it costs too much. I may be able to reduce the cost or the weight of some design and come up with something better. Similarly, I may just be scouting around for something new. Someone has suggested, can't we do this? And the answer may be, I really don't know, but let me use some finite element analysis. I'll come up with some ideas. I'll see if any of them work, see if any of them make sense. Other times, you have a concept and you have no idea whether it's going to work or not, or even might work. So you could do some finite element analysis to gain some insight into the concepts, and you can find directions to it, general trends. Does making it thicker always make it worse, or does making it thicker make it better in some situations? Does it last longer if I do this, or does it not? So there's where we can use finite elements. The basic way to do it in the design process is to come up with some geometry, create a geometry. This may be a concept. There's fillets and everything drawn on this one, and you may not have a concept that's fully formed, but you give it some material properties. You pick a material, you create a mesh, you apply loads and constraints, you run the analysis, and you look at the results. The results may be perfectly good, and you say, great, my first guess was great. Otherwise, you may come back here and follow the line, modify my geometry, and repeat as necessary. I may modify the geometry to make a better thing. I may decide I need to make it out of a different material. I may have decided for whatever reason my mesh was insufficient. I may say, wow, my design was great. Can I put a higher load and make it work? Can I hold it in a different way and make it work even better? So if I can do this and iterate multiple times, I can reduce the chance of failure because I have a lot better feel for how my part's behaving. I can improve performance if I have time, and I can optimize for cost. I'll talk about some assumptions too. People often don't think about all the assumptions that go into finite elements, but there's actually quite a few of them that go in, and people say, well, do you match a test? That always seems to be the gold standard. And sometimes you match a test and it's great, and other times the assumptions made by the test and the assumptions made by the analysis may be a little different. For instance, I may be representing it as shells when it's really a solid. I mean, everything is a solid piece, but I may be representing it as shells. That may be a really good idealization, or it may not. My geometry may include bolt holes. It may include threads on bolt holes. It may include chamfers or fillets that either are or aren't in the real product. So at some point we're idealizing. We're saying they don't matter or they do matter. My properties, people think of them as constants, but how thick is 1-inch steel? Is it actually exactly 1.000 inches? Probably not. It varies a little, especially if you're using preformed beams. The published values for beam properties by places like AISC are published, they're averages of what's actually on the market. It doesn't necessarily mean that's exactly what your beam looks like. Similarly, materials, some are pretty uniform, like steel and aluminum are pretty uniform. Although if you're looking at failure, who knows where that's going to be. Other materials like elastomers and plastics have very, very different properties, and you're making an assumption that the property that I'm using in my analysis actually represents what it's made of. Finally, we're breaking a continuous structure up into a finite number of elements, and we're meshing it. And there's some approximation and some assumptions that go on in there. Again, if you do these good, they're good. The interactions with your environment, the boundary conditions, loads, constraints, those are all, to a degree, assumptions. If I have a tire sitting on the ground, what is the pattern that the tire contacts the ground when it's loaded? I may be able to measure that and know exactly what it is, or I may make some assumption that it's a square, that it's an oval, or some other shape in order to come up with my analysis. We're also assuming that you're using the appropriate physics, that if I have a nonlinear problem, I'm really doing a nonlinear analysis. If I have a dynamics problem, I'm doing a dynamic analysis. So those are all assumptions. Any of them you make, write them down, put them in the report. Some of the idealizations we can make, shell models are all plane stress. You're assuming there's no stress out of the plane. Plane strain is another interesting idealization. I can say I have a really long structure that's constant for a long length. I can model just a slice through it and get an answer for the whole thing just by modeling a slice through it with a plane strain assumption. Similarly, in the 3D world, if I have a structure that looks like beams, a radio tower, an oil derrick, for instance, I can do a beam simulation. I don't need to go out and model every little detail of it. A beam simulation may be perfectly good. Symmetry and anti-symmetry. If it's loaded symmetrically and the structure is symmetric, model half of it. It'll run a lot faster and save you a lot of time. If you have a structure that's primarily thin pieces, sheet metal.
I apologize. I forgot my mic was muted. Hi, thank you for calling Autodesk technical support. How can I help you?
Oh, hold on. So plate or shell models are something else that's...
That was kind of funny. Sorry about that, Bart.
Sorry. The plate or shell models are for thin structures. You can technically model them with solid elements and mesh them to death, but you need lots and lots of elements to get your answer, and they're not going to be very good. So a 3D simulation and plate shell simulation might be a better way to do it. On the other hand, of course, you've got 3D solids. 3D solids, you're going to have to model them with 3D solids because they are. When I look at the structure on the left, there's really no good way for me to approximate that as anything but a solid. So that's what I'd have to do. So what can I do with all the finite element stuff? You can do lots of things. Almost anything that can be described mathematically, you can do a finite element analysis on. It's commonly used for stress analysis. It's commonly used for thermal analysis. There's a lot of people who use finite elements for computational fluid dynamics. Radar cross-section, how visible things are to radar, is actually a mathematical equation, and you can write a finite element code to solve radar cross-section problems and predict how much something's going to show up on radar. Lots of things you can do. In-CAD has a whole lot of things that it can do. It does linear statics in the structural world, buckling in the structural world, normal modes. Those three are things that an awful lot of different codes do, and most finite elements do them to one degree or the other. In addition to In-CAD, I can do pre-stress statics and normal modes. I can do linear steady-state heat transfer. I can run composite materials. I can use large assemblies of multiple parts that contact each other and bump into each other. I can do thermal stress problems, where I've done a thermal analysis over here and used the results from my thermal heat transfer to come up with a stress analysis. On the farther end of it, In-CAD is capable of doing nonlinear statics. Down here it's doing nonlinear transient response and linear transient response. A subset of that is an automatic impact analysis, where I drop something. It's technically a nonlinear transient response, but you can set it all up automatically. In-CAD will do heat transfer. We can do random response. We can do enforced vibration, frequency response. And in addition, in-CAD includes, and Nastran include, a number of advanced materials, such as concrete, soil, and hyperelastic materials, such as this rubber boot in the little picture down here that we're pulling on and sort of inverting. So I was going to do a quick little show here of in-CAD in action and do a quick little demo here. If any of you have done some of the in-CAD training, you may have seen this model. This represents a tank. And the tank it was modeled in Inventor as a solid, and then we broke up the surfaces of it. The purple area of this tank is actually is actually where the fluid is sitting, and the parts up here, these two surfaces up top, are not. So I want to analyze this. I want to fill it with fluid, put a hydrostatic load on it, and run it, and see if my tank is any good. So the first thing I do from Inventor, in 2016, we've put it into the environment. So when I click on the Environment tab, there's now an Autodesk Nastran tab there. And if you've used in-CAD before, you'll look at this, and it looks pretty familiar. There's a couple things that may have changed, but for the most part, it's the same as it was in 2015, the way it looks. So first thing I'm going to do is I'm going to start with a material. This form changed a little bit. I'm going to select a material. I'm going to pick out of, let's pick out of the Inventor material library. I'm going to pick the stainless steel. Close it. It's loaded it over. It's given it a name. It has a G value, and the G values aren't always consistent with the E and the new values. So I'm going to delete that in this case and let Nastran calculate its own G value. But there's my material. I'm just going to say OK. So now I've got a material. Over on my model tree here, I see a material. I have stainless steel. Now I've got to create our physical properties. And I don't have solid elements. I'm going to model this with shell elements here. They're made of stainless steel. And they're going to be a thickness over here of 0.1 inches. So 0.1 inches is my thickness. And I'm going to associate geometry to them. And so I'm going to tell it that this surface, this one, this part, and the bottom of this tank are all made of stainless steel 0.1 inches thick. I'll say OK. So at this point, I'm really ready to mesh, but I'm going to hold off on that a minute. I need to constrain my model here. So how am I going to constrain it? This tank is actually a quarter model. So along this side over on the left, I'm going to put one constraint, and the side over on the right, I'm going to put another. So I'm going to start, and I'm going to put a constraint. It's going to be a symmetry constraint along here, and along here. And that direction is X. So that is X symmetry. So that's going to let it slide in plane, but it's not going to let it move out of that plane, the YZ plane. So I'll say OK to that. And then I'm going to create another constraint here. Then it's going to be the other side along here. And this edge of the bottom, oops, sorry. This edge of the bottom. And that one is in the Z direction. So I am going to use Z symmetry for that one. And you can see when I click on Z symmetry, it chooses the appropriate degrees of freedom. So TZ is not, and the RZs are constrained. So I'll say OK. And so now it's not going to move in the X or Z directions because of the constraint. But at the moment, it's still free to move in the Y direction. So I'm going to create one more constraint in the Y direction. A little constraint here. I'm going to pick the bottom surface so it doesn't move in the Y direction. And if I choose free, it gets rid of everything, and then I can just pick TY, so it's only constrained in the Y. So, okay, I'm good to go with that. That's pretty good. Now I need to load my tank. I'm going to load it with a pressure because it's a hydrostatic pressure. I already said the pressure is going to be located on this face, the side face there, and the purple face on the bottom. But in this case, I have some advanced options. Because it's a hydrostatic load, I'm going to want the load to vary as it goes down the edge. So I'm going to choose a variable load over here, and I'm going to pick a target point up here at the water-free surface and a target point down at the bottom of the tank. I'm going to add those to my list. If the free surface, it has a pressure of 0 because it's a free surface. And whoops, let me go back to my load here. I hit my thing too fast. Down here at my Y of 0, I have a pressure of 3.032 psi, which I calculated because it's 48 inches high, and that's what the pressure is in psi. So I'll say OK. And one other thing I forgot to do here. I have to give it a load magnitude. I'm going to give it a load magnitude of -1 because these surfaces are oriented, so a positive 1 would be a pressure trying to crush it. A -1 is a pressure that tries to expand it as though it were filled with water. You can see the load now, once I've done this correctly, that the arrows are big at the bottom where I've got the full 3 psi, and they get smaller as I go up, representing the hydrostatic pressure. So that's what we got. At this point, I'm pretty much ready to mesh it. I'm going to mesh it with a global size of 3. I am going to use linear elements because the linear shell elements in Nastran are very good elements. There's no point in going to parabolic shell elements. I'll check continuous meshing to make sure that all these edges work together. And I'll say update. And boom, boom, boom. It has created a mesh. So I now have a mesh on my model. I have a load. I have a constraint. I have materials. I have properties. I am ready to run. So I'm going to run this analysis. It's set up as a linear static, so I'm just going to take all the defaults and run my model for a linear static analysis. It whips right on through here. Linear static is pretty fast. Nastran's solution is complete. And the results, this changed a little bit for 2016. I can plot my displacement contour right away, and I can see sort of an odd displacement contour here. It bulges out at the bottom, which is what you sort of might expect, but the top edges don't look quite right. I would think my top edges would move out a lot more. I would think that this would push it and do it, but I don't know. I have to think about that. I'll have to think about whether that makes sense or not. I have a peak displacement of 8 inches here, and when I think about that 8 inches, I've built tanks like this before, and I've looked at them, and I know that 8 inches is not the right size. So I've actually tested these, and I know it deflects a few inches, but it's not 8. Let's come back to that. I look at my von Mises stresses on another plot here, and I'm seeing stresses of 150,000 psi. That's an awful lot of stress. I find myself looking at this going, you know, I've got a lot of loading normal to the things, and things are constrained. Is it possible that I have a nonlinear problem? So let's investigate that. Let's go up to my analysis here and edit my analysis. And I'm going to change it from a linear static analysis to a nonlinear static analysis. I'll say OK. I'm going to take all the defaults on this, and all it's going to do differently is it's going to let the grids move and physically move. So if that 8-inch deflection was there, it's really going to have an 8-inch deflection. But we'll see what it gets. So we're going to run it now as a nonlinear static. The first thing that's different is it comes up with this little iteration window, and it's divided by default into 10 increments. So you can see it counting increment 8, increment 9, increment 10. So it's come out and finished 10 increments. It's going to finish writing the data. And you can see right away that the shape is a little bit different. When I do this, again, let me go look at my results again. When I display, let's look at deflections first. I'll look at my deformations and display them. I can see now that the top edge is actually moving out. And to be honest, that sort of fits more with what I'd think I'd see in a thing. And the reason is, when you run this with a linear static, you don't get any stress stiffening. Whereas in reality, when I load this, this tank, I get a little stress stiffening, and as it starts to bow out, it takes more load. So this shape makes better, plus I have a peak deflection of a little under 4 inches, and that jibes with what I knew before. If I look at my von Mises stress here, my von Mises stress, they're down to 70,000, and it's all located along this corner. And so the first thing I think about looking at this is that, wow, 70,000, that's actually over yield. So maybe I should include some material plasticity to see how this tank really behaves. So I'm going to do a quick little modification to my model over here. I'm going to go in and I'm going to edit my material. And I'm going to click on the nonlinear bot here. And I'm going to cheat. I'm going to use a bilinear elastic plastic. A tangent modulus I'm going to use is, so when it starts going plastic, it's going to have 1/10 of the modulus. And my initial yield on this is 50,000. So I'm going to give an initial yield of 50,000 von Mises stress. So my 70,000 is a little bit over. I'll say, okay, I've updated. I've got a nonlinear material. I'm running large deflections. Oops. So I am ready to run the job again. Once again, this is a small problem. It runs really fast. You may notice I'm getting into double-digit iterations, but I'm still working quickly through 5, 6, increment 7, increment 8, increment 9, increment 10, and it finishes increment 10. And now you can see here, before I close this little window, the von Mises stress is now about 55,000, and 55,000 is a whole lot more what I would expect if it yielded a little bit. My deflection has not changed, which you can see if I go in here and plot my displacement. My displacement is basically still 3.7, so adding plasticity hasn't changed it. Well, that leads me to believe that the plasticity is not having a tremendous effect on anything. So let's take a look at how much there is. There's something down here called shell effective strain. It says elastic. It's really plastic. And I change it to that and run it. And look at this. There's just a little tiny area up in the top of my model that yields just a little bit. It yields just a little bit. And by yielding just a little bit, it allows the whole rest of the structure to remain unstressed. So you have to sit back and look at it at this point and go, gee, do I try to reinforce it? Do I just let my tank bend a little bit? But anyway, that's sort of the workflow you can go through in InCAD. And that's InCAD in action there. So with that, I'll close that out and I'll get back to our regular presentation and have a call for questions. Is Andrew there?
Awesome job, Bart. So we did have a couple questions come in while you're presenting there. So one of them was Daniel was asking about where to find Nastran In-CAD 2016 versus 2015. And I think you highlighted that where it's now on the Environments tab versus its own tab. So it's just a change there that we made to improve performance within Inventor.
And I'll attest that the performance improvement is significant. Moving it to the environment hides it a little bit, but it definitely makes it run faster.
So we had another one from Daniel here. I was wondering, how does he model a ball impact? So I think we would use the impact analysis feature. So I don't know if you could bring up Inventor, Bart, and we could just take a quick look at that.
Yeah, there's two ways. If you're going to do a ball impact, there's two ways you can do it. And one is to manually set everything up. And it would be a nonlinear transient analysis, which is down here, nonlinear transient analysis. And with the nonlinear transient analysis, you could manually set up the contacts and say, this will contact with this, it's moving this fast. You can give it initial conditions so that the ball is moving at a certain speed before the contact. And then you would choose time steps in your nonlinear setup in order to have a, there, yes. You choose a number of time steps or increments in order to simulate the event. An alternate way to do it in InCAD, which is really pretty slick, is over here when I was editing this, you may have noticed that there was a note down here called Solve Impact Analysis and Set Up Impact Analysis. And this is a little feature that Nastran had built in a few years ago. And what you do in this one is you give an initial velocity, in this case to the ball. You tell it the projectile is the ball, and you pick the ball. And then you tell it that the projectile is following this path, and it's going to hit something else. And really, that's all you have to do. And InCAD will take care of setting up the initial transient, setting up the contact, setting up the velocities, setting up the initial conditions, and running it all itself. So a ball impact or something that's actually impacting can be done with this automated impact analysis really a lot easier. The projectile path would be a CAD curve. So you draw a line in the CAD in Inventor, or SolidWorks, I guess. You draw the line from your projectile to the piece that it's impacting. So that's how you do that ball problem.
Great. So it looks like we do have several more questions coming in here.
Okay.
So Lee was asking, can we do this within AutoCAD? And we can't. So Nastran In-CAD only functions within Autodesk Inventor and SolidWorks. So it's an add-in for both those products, not AutoCAD or any other CAD packages at this time. Another question from Thomas here, asking, so when if I understand it correctly, In-CAD is just the name to say that it runs In-CAD, but the real calculation will be done with the Nastran solvers, and that's correct. So we use
absolutely.
Yeah, we use the Nastran solvers behind the scenes to solve the analysis, but it's called In-CAD because it's within your CAD package.
Yeah. In-CAD is technically the front end, but it includes the solver of Nastran, so exactly right.
So another question, you had asking about reporting functionality within In-CAD from Carol.
There isn't a ton. There's the ability to do some reporting, and let me go into here. There's some reporting dealing that you can do. It's just not a lot of stuff. Actually, I'm thinking you can't do it from inside of In-CAD. Now that I'm looking at it, I can create a whole series of reports, but I don't believe I can create a report from inside of In-CAD, unless you know any better.
I think it may be through the default settings.
There we are. Yes, there it is. I knew it was there somewhere. Yeah, there's a number. It's a fairly basic report. You give it titles, you give it units. At the moment, it's only set up to do an linear static, and it generates a glossary of terms, a summary of the results, and you pick what they look like, documentation of some assumptions that you list, pictures of the model, boundary conditions and loads. You pick a number of plots to put in the result, and when you're all done, you hit generate the report, and it generates that report. So it's a very basic capability, but it is there. And at the moment, it looks like it only does it for linear statics from within In-CAD. I think that's something on our list of things to work on. I really don't know, though.
We have another question here from James about the progressive ply failure analysis module. I think we had talked about this a little bit earlier, Bart, off air, that we have the SciWu and two other.
Yeah, we have a number of different failure theories, and we have Hill, Hoffman, SciWu, Puck, LARCO2, maximum stress, maximum strain. There's a number of different composite failure theories we use, and as long as you put in the failure theory and turn on progressive ply failure, it will use whatever theory you've specified with whatever allowables you've put in, and as apply reaches a failure index of 1 and indicate it's failed, it will be changed over to the stiffness of that ply will be reduced by the amount specified on the stiffness reduction factor. So it's all available within, it's actually all available within In-CAD. You set up all those little factors and allowables and reduction factors, and progressive ply is turned on using a parameter. I think the parameter is called progressive ply. No, comp failure. It's a parameter that turns on progressive ply failure. And as long as you have all the allowables, it will fail ply by ply by ply. What else?
It looks like we do have a slew of other questions here. So Carol's asking about how to check convergence in Nastran In-CAD.
2 ways you can do it. One of the things we always generate is an error plot, and I don't know if I have it. I don't know that it does it in the nonlinear ones, but it's one of the results is a mesh error plot, and I don't think we do it for nonlinear analysis. I think it's, oh, there it is. Yeah, there it is. Mesh shell max mesh convergence error. So it'll give you a mesh convergence error after you've run it, and the method of that is simply comparing element A to element B and saying element A says it's 10 psi and element B says it's 100 psi, so they differ by 90 psi. So along that boundary between the 2 elements, you have a 90%. It's not necessarily a 90% error, but you have a change in stress by 90%. So that's one way to check the convergence. A way that I personally like to check convergence is, let me plot some von Mises stresses here. Let's display von Mises stresses. There we are. Okay. And say display. One of the things I like to do is I like to go down and change my contour to an elemental contour. And so this is just looking and averaging the stresses based on an element centroid basis. And I can go down here and change my averaging and turn my averaging off. And what that does is it plots each element with its own centroid stress. So when I look at this, I see they're all red all the way down this edge here. And right next to them, they're blue. And that tells me that I'm going from a stress that's fairly high, 55,000 roughly, somewhere around 50,000, down to a stress that's down here in 20,000 in one element. And I had a professor who used to call it the 3 contour rule. And he said if you see more than 3 contours across an element, you don't have enough elements and your mesh is not converged. And by looking at this, elements next to each other should generally have roughly the same, you should see a gradual rainbow like you do here, red to orange to green to blue. You don't want to see it jump. So using stress averaging is a good way. When I turn it on and off, the contour shouldn't change all that much. And in this case, it changes quite a bit. So this tells me that I obviously don't have a converged mesh here. And of course, you can always just double the mesh density. I can go up here to my global, change my size to 1.5, and run it and see if I get the same answers. That's probably I call that the brute force method of mesh convergence. So that's what's available to you.
Okay, let's see. I think we had a couple other questions. Let's see. All right, so Thomas had a question here. So how can I see if I have a linear or nonlinear situation? Is it just to look at the calculated results and then you decide, or is there some kind of rule or guidelines?
There's no firm and fast rule and guidelines. There's certain situations where you absolutely know you have a nonlinear problem. When I ran this and I saw my stress was over the yield point, that told me right away that I have a nonlinear problem because my material's yielding and it's going to yield. So that's a clear indicator. The bouncing ball problem, the impacting ball we talked about, you have contact. The boundary condition is changing during the course of the analysis. That's clearly a nonlinear analysis. The ball may be hitting and bouncing off. It's moving a significant amount. That's also a nonlinear analysis. Those are easy. Those are easy to tell you're nonlinear. Some of them, like this tank, are a lot more subtle. My favorite nonlinear one is if you imagine a plate that's fixed on all four sides. One of the assumptions of linear theory is that you don't get stress stiffening. So if I have a plate fixed on all four sides and I push down on it, the plate has not actually moved out of position, so there's no bending in the plate and there's no tensile force in the plate. So the only thing that resists the deformation is shear. So if you have that plate fixed like that and you put a pressure on it, you get a really, really large deflection because there's only shear. When in fact, you have a lot of stress stiffening, and also once it deflects, it starts to bend and you end up with bending stiffness. This tank is sort of a subtle one because the tank actually moves and you're developing some bending stiffness because the tank sides do move out substantially, but you're not, the shear is still causing that big deflection of 8 inches that we saw. So sometimes the only way is to run it linear and run it nonlinear and see if there's a difference. If there's a difference, then it's a nonlinear problem. The nice thing is that with in-CAD, I can do a fairly quick job of just changing it from linear static to nonlinear static and taking the defaults. Large deflections, which cause the stress stiffening, are something that Nastran nonlinear, in-CAD nonlinear handles very, very well. So it's not often a massive undertaking to do a quick check to see if it's a large displacement nonlinear. So there's no hard and fast rule except when you absolutely know you've got nonlinear. But sometimes you have it and don't realize you do.
All right, so we have another question here from Darren asking if we use a P or H method for our mesh.
H method, all H method. We have quadratic elements available, but we only do second order elements and we don't change them during, so it's all H method.
All right, the next one, let's see, James is looking how to change the mesh size for different parts. So I don't know if we can show that too well here because we only have one part.
Yeah,
analysis.
I'll address it. The way you do it is up under the table up here. The mesh table will have a separate entry for each part, and I can put a different mesh size on each part so the different parts will have their own mesh density. And as long as you have it broken up into parts, that's a decent way to do it. Another way to do it is over here under my mesh model, and actually do this. There's a button down on the bottom here that says Add Mesh Control, and I can pick a face here, for instance, like this face and this face, and tell it I want a mesh density of 1.5 on those two faces. And now when I update my mesh, it puts a 1.5 inch mesh on those areas and the others. And so that allows me to control edges, faces, and points. If I want to change the size on a whole body, then I need to use the separate part. That separate body needs to be a separate part. But I can control the face meshes and eventually the interior meshes using mesh controls. I don't know. Does that clear it, Andrew? Anything else there?
I think so.
That's a good start.
Yeah, so we had another one
in the future to go in deeper.
Okay, great.
Yeah. We had another one here from Carol about convergence. I don't know if you could show a little bit about the modifying the convergence tolerance for the analysis. I think she had a couple questions about that.
Is this for a nonlinear analysis? I'm assuming this is for a nonlinear. Okay, let me talk about that. When I go into my nonlinear analysis, I have the advanced settings that come up. And the advanced settings, by default, Nastran divides everything. Hold it. By default, on a nonlinear static, we take it into not 10 increments. 10 increments is great. I didn't do it, but I'd always turn the intermediate output on. But more increments generally makes it easier to converge. On the advanced settings, and I think we're going to do a webinar on this a little bit later at some point on getting nonlinear ones to converge but quickly, there's 3 different criteria: displacement, load, and work. And by default, Nastran converges on load and work. And whenever you run one of these jobs, and let me see if I can find this one that I have. It's going to be D. Let me look at my out file here. Whenever you run this nonlinear job, in the output file, it has a list here that hopefully people can see, which is my convergence iterations criteria. And if I look through it, here's my displacement column, my load column, and my work column, and it has the absolute error and the percent error, or I should say the absolute convergence and the percent convergence. And what it's trying to do is minimize the error down to a point where it's acceptable. And on the advanced form over here, where I have the values over here, if I leave them blank, I get the defaults. And you can look up on the documentation for either the NL parm or the T-step NL entry, and those will tell you what the default tolerances are. I think they're like 10 to the minus fifth or something. And as I walk through here, I can look and see things. Sometimes when you run a job and it isn't working and it isn't converging, you'll look at these and you'll say, boy, work has converged up here and displacement converged up here, but load just isn't converging. And that's entirely possible because there's whole classes of problems where the load will never converge or it will converge very slowly. So if you have a situation like that where 2 are converging early and 1's not converging, you can always go over here and change it. If I just check them, the convergence criteria will adjust and use the other one. So it lists all of these and it shows them all converging, but the fact that, let's see, displacement, the fact that displacement converged didn't trip it to stop because it wasn't being used. If I did this, it would converge here, but it still would converge at the same spot. The values of these are tiny. If you have really hard time with convergence, you can make them larger. If you make them larger, your answers will be less accurate, and it's sort of up to you to figure out whether the error you're getting is acceptable. It's sort of hard to tell. Sometimes you can run the job with an increased error tolerance and you start looking at it and realize it's all bogus. Other times you can hardly tell. So that's about all I can say about nonlinear convergence. What else we got?
Awesome, Bart. So I think we've answered all the questions for everyone remaining.
Okay,
we are
great.
at the top of the hour here.
Great.
So if anyone has any further questions, I definitely recommend that they can go to the Nastran In-CAD forum and post any questions there, and we'll try to take a look later this afternoon if we see anything. We'll also be sending out a survey once the webinar ends, asking for your feedback and if you have any topic suggestions. I think we do have a list of some of our upcoming topics available on the Nastran In-CAD forum. There's a post there at the top regarding the webinar series. So again, I want to thank everyone for joining us this morning or this afternoon, depending on where you are, and I hope you guys have a great day, and we'll see you in 2 weeks.
Thanks for coming.